Swift concurrency's actors, they are a complicated subject, and every time you think you just got it, things will get a little bit more complicated, and you might be somewhat more confused. My name is Donnie Walls, and in this video, I would like to take a look at actor reentrancy. If you're not subscribed to the channel yet, go ahead and subscribe right now so that you're always up to date with the latest videos that I upload. Now, actors in Swift, the topic at hand. When you first start learning about actors and you find some folks sharing definitions like actors protect shared mutable state by making sure that the actor only does one thing at a time. That summary is actually pretty accurate, but it misses some nuances. An actor does one thing at a time, and it does that to protect our mutable state, but that does not mean that they act like serial queues. In other words, it doesn't mean that they perform their work atomically. If you're not sure what atomically means, there's a video, a little post in the description down below that you can read where I explain what atomicity is in programming. Now, in this particular video, you don't need to fully understand what atomic means, but essentially, the very short version is an actor does not execute a function from start to finish without interruptions, if that function is async, and you await something inside of that function. So there's some nuance to it. But in this video, we'll see exactly what that means and how it works. Actors are very commonly used in a context where you have some model with mutable state. That model has to be a reference type, and you're struggling to make it sendable, for example, or you don't want to write your own concurrency save mechanisms around that class. And the easiest way is to just make that class into an actor. And if that's what you did in your project, you're completely fine. Okay, whatever you learn in this video, you're not in trouble. Actors are not going to ruin your life, per se. But for simple models, they're perfectly fine. Let's take a look at a very simple example actor right here. This actor you're going to see in a moment will cache data objects using UUID as keys and then data as the value, and here's what it looks like. This actor is super simple. Anybody that uses this actor can directly access the cache variable and mutate it as needed. While this feels kind of nice, point one, I don't like it as an interface. I want to be able to change the underlying storage mechanism. And point two, this also wouldn't really work in a strict concurrency setting because it's going to tell you that you can't just mutate actors' state from other concurrency contexts, and really it's going to be a big mess. So what you should be doing is adding a read and write method around that cache so that you have these two functions that users can use to interact with your actor and to interact with your underlying cache without exposing the actual details of how you're caching stuff. So here's what that looks like. We have a private var cache. We've got two functions to our actor, read and write. And at this point, everything works completely fine. We're not looking at any reentrancy related problems right now. Instead, what we have is a very simple to use caching object that we can actually put data into and get data out of. But let's complicate matters for a little bit. All right, let's imagine that our cache can leverage a remote external storage, like a web server, and it can use that to back up data and to get it back at a later time. It could be very useful if you're having multiple devices, for example. You're going to pass the backend a UUID, and the backend will just tell you, I have data for that UUID, yes or no. Very, very simple. So whenever we ask our actor, do you have this value locally? The actor is going to check whether it does. If it has the value locally, it's going to give you that. If it doesn't have a local value cached, it's going to go to the network, see if the network has that value cached, and then return that. And if that happens, and the network does have your data, we're also going to cache that data locally so that the next network call that we make can actually leverage that data. So let's go ahead and see what the actor looks like when we do that. And there's actually a ton of code here, and I don't really expect you to actually read this. What I want to do instead is go over to the computer where I can do a little demo of what this actor looks like and how it works and how it actually sort of messes up our data consistency and how actor reentrancy can actually look. So let's move on to the computer. Okay, so what I have here is a slightly reworked version of what you just saw on the slide, because to be honest, I made that extra lengthy just so that it would look like I really needed to do this demo. which I still would have had to do anyway. Any point. So we have our actor here. It's a data cache actor, and it has our private var cache still, but now it also has a dependency on a remote cache object, which has a read and write function that are both asynchronous, right? So that's our network object. And whenever we call a read function, we print a little something to the console, and when we're done reading, we print another message to the console. We await our remote cache's read data. If we get something back, we return that. And I should actually go ahead and fix a bug here immediately, because of course what we want to do is add our newly fetched data to our local cache. If we don't get anything back from the server, we'll just return nil because we don't have this data. Simple enough. And when we write something, we tell the server that we want to write this new data, and we also want to cache that locally as well. I also have a little test here, right? So that's a little task group that adds 5 tasks to itself so that we can run our code concurrently for 5 calls to our cache. Notice that I'm using a pre-created UUID here. My server has some values or a single value pre-populated so that we can actually go to the cache and get something back from the server. Okay, so that's the sample code. Let's go ahead and run this and see what happens. So when we hit this button, run the example, that's when I'm going to kick off my 5 concurrent read calls for my actor. And what we see here is interesting. This either makes total sense to you or it's quite surprising. So what happens is our local cache is asked for a value, and then it goes to remote because it doesn't have the value locally. And it does that again and again and again until at some point the remote cache returns a hit and then our local cache read finishes, right? So that happens 5 times. So what's surprisingly happening here is that even though our actor is supposed to do only one thing at a time, we're somehow running these read calls here concurrently, which is strange. It's not what we might actually expect, because whenever we hit the read function, we immediately go into the cache. And then the first thing it'll say is, Donnie, you have a bug here. And I know, I just realized that I do. So let's go on ahead and say if let data equals cache key return data, right? Maybe we just weren't reading this value locally and that's why we're solving the behavior we did. And I know that that's not the case, but I want to show you anyway, right? So we're still getting the exact same behavior. So failing to read our local cache is not our problem here. Our problem is something else. Our actor only does one thing at a time, but as I said at the beginning of the video, an actor does not necessarily do things atomically. So it might not execute a read function start to finish without interruptions, and here's why. The read function here is asynchronous. And so it's going to run, and then we hit this await. And at this point, the actor can choose to either do nothing or to handle the next call to the read function. And it chooses the latter. So it will execute the next call to read. It's only running actively one call at a time, but it will actually at some point have all 5 of them in flight, if you will. It'll be awaiting all 5. And we don't want that. And this is the exact problem that we call actor reentrancy. What we might want is for this function to run start to finish without interruptions, so that the second call to read actually finds the local value and returns that instead. Okay, so you've seen the problem now. Let's go back to the presentation for a moment before we see how we can solve this issue. So the problem here that we saw is not a problem with actors. It's not a bug in Swift concurrency. It's actually a feature. And it is a feature that exposes some possible issues with awaiting something inside of an actor. Because as I said, an actor does one thing at a time. But as we call functions on an actor concurrently, the actor will start stacking these functions or these calls up in something called its mailbox. And so whenever an actor suspends one of its functions to await an asynchronous operation like we're doing, an actor doesn't like to do nothing. So it will look at its mailbox and see that there's another function call in there that it can actually start running so that it keeps making forward progress. It doesn't like to just sit by and do nothing, because that would block the actor for a very long time and it would probably slow things down by a lot. So instead, the actor makes progress on the read function and it keeps hitting awaits and suspension points, and it starts executing new messages until one of these suspension points decides to resume. then the actor will actually make that the very next thing that it does, right? And oftentimes this is fine. Other times this means that there's some state that you verify before you hit an await inside of your actor, and you just might have to re-verify these things before you proceed after your await. Or like in this case, we need to do a little bit of work to make sure that we can actually prevent multiple network calls for the same resource to be made in parallel, right? So we don't want to make any network calls when we know that we're already making one. There's other more complicated scenarios, like making an actor behave like a serial queue, that are even more complicated, but there's just one situation that I wanted to highlight in this video, so we're going to look at a solution for that right now. So we're back at the computer, and let's see what we need to deal with in order to correctly handle all of the different scenarios that we might be in. So the first scenario is we call a read function, and we already have a load operation for this resource, right? So we're already fetching data, and we might be able to reuse that. Scenario 2, we already have a local value for this key. In that case, we don't need to go to the network at all. And then the third scenario, we need to go to the network, right? And so to implement this, we need some way to cache in progress tasks. So to do that, we'll add a nested enum to our data cache. We'll call that loading state. And we'll have a case in progress, which means that we are fetching data. And that will have an associated value of task with optional data, and it will never fail. The data needs to be optional here because our network might actually tell us that there's no data available. So the task could produce a nil value. We'll never fail the task just for convenience. In the real world, you might actually want to have error handling here. For the video, I do not. The second case that we need on our loading state is completed. And if we're completed, we'll have data. It's going to be non-optional data because we only consider successful fetches with actual data to be our completed case. So scenario 1, we already have a load operation for this resource. We'll say if case let dot in progress task equals cache key. Oh, we actually need to update our cache property here to hold values of UID as a key and loading state as a value. So if the value for the given key is an in progress task, we will actually return await task.value. This allows us to take an unstructured task that somebody else created and just await the value for that task. So if that task is already running, we're just going to get the result of it. We're not going to start the task again. We're not going to have 2 tasks, not 3 tasks. We'll just have 1 task running, and we can just wait for the result of that task, which is quite neat. Now, in the second situation, we already have a local value for this key. We need to update the logic here a little bit to say if case let dot complete with data equals cache key, we'll just return data. And did I call that completed? Yes, I did. Okay, so that's the second scenario. That's simple. The third one's a little bit more complicated. We need to make a let loading task, which will be an unstructured task that produces optional data and never fails. And inside of that, we will attempt to await our remote cache's read function. If that failed for whatever reason, we'll return nil. And if it worked, we return data. Okay, so here is the really tricky and kind of strange dance that we need to do. The first thing we should do is cache key equals in progress our loading task. And so what's interesting here is that the loading task starts running immediately, but we're not awaiting it yet. So it's just running on its own. And then we assign it to our cache key. So our actor's state currently holds the in progress task in its cache dictionary. Now we say let task result equals loading task, await loading task.value. So this is where we suspend. This is where we actually hit that suspension point where the next function call can come in and actually see that our cache key is an in-progress task, and so it will start awaiting that task too. Now, when we get the result back and let task result gets a value, we can actually say cache key equals completed task result, right? Because the task result is our data. And we actually need to wrap that into an if let here, or let's make it a guard. So if we get a task result, we use it, and otherwise we return nil. Right, and we should actually clean up our dictionary here to also have a nil value. Right, so if we could not obtain a value, or if we if we couldn't obtain a value, we want to nil out the operation from the cache because we don't have an in-progress task anymore, and we also didn't get a result. So we just want to set the cache key back to being nil. Okay, so we do have a value. We say cache key equals completed task result, and then we return task result. So that is our data. All right, this is a whole lot more code than we had before, but as I mentioned, this will actually ensure that things work correctly. We do need to update our write function as well. Our cache key now has to become completed data because we don't go to the network to fetch stuff for things that we have locally. Now, one more time, what happens when this function gets called? The first time it gets called, or actually before we explain this, let's look at if it actually works, right? Because I don't want to be explaining code that doesn't work. Okay, so we hit the run the example, we do the 5 concurrent calls, and we see that there's 5 calls to the read function quickly after each other. And that makes total sense, right? Because our actor is going to run this function, cache read called, and then for the first run, we do not have an in-progress task. We do not have a completed task, so we make a loading task and we start awaiting that task after we put it in the cache. So that's the first function call. Then the second one prints cache read called, and then it says, oh, hey, there's an in-progress task. Let's go on ahead and await that. Then the third, fourth, and fifth call all do this exact same thing. Then we see that we have an attempt to read the remote cache, right? And so that happens right here. We try to read from a remote cache. We go to the server, and the server then tells us that there is a cache hit. That's perfect. That's exactly what we wanted. Now, once that finishes, then all of the calls to read will actually have their tasks completed. So all the awaits are going to fulfill after each other, right? One at a time, because the actor only does one thing at a time, but it doesn't do things atomically, right? So we have this read function, we get into the read, we hit an await, we get the value, we return the value, and then all the other function calls also return the exact same value. This is complicated stuff, and it will require you some rereading and some rewatching of this explanation to actually fully get it. But the magic here is in being able to cache this in-progress task so that subsequent calls to read while we're awaiting the result can actually reuse the exact same task that we have already made to prevent multiple network calls from being made, as shown here in the console. Okay, let's go on ahead and wrap things up. Actor reentrancy is an interesting problem, and it can lead to some subtle and sometimes really hard to detect bugs. Luckily, in this case, it was pretty easy to see the bug, and it was not too complicated to solve if you know this as a possible solution for actor reentrancy. Actor reentrancy really only happens when you start defining asynchronous methods on your actors, and sometimes, like I said, all you need to do is reevaluate some assumptions that you have made before an await. Other times it's more complicated, like having to cache a task object, or if you're trying to implement something like serial queue behavior, things get really, really complicated. Actor reentrancy is not a bug in Swift concurrency, but it is somewhat of a frustrating problem because there's no built-in mechanisms that help us alleviate reentrancy related problems at this time. So hopefully in a couple of months, Apple will announce something like a serial actor where we can actually ensure serial queue behavior. Now, my question to you is, do you use actors in your projects? And have you had any reentrancy related problems? And did you manage to solve them? If so, let me know in the comments down below. If you're not subscribed to the channel, make sure you do that right now. Hit that notification bell so that you are always up to date with my latest videos. And with that, I'd like to thank you for watching, and I'll hopefully see you in the next one.